this intro you wrote, just a small intro. All right, good morning, everyone. Good morning. Welcome to our first ever Cyber Research Showcase. We have a lot of research presenters. They'll be presenting all day. Schedule's outside. Let me introduce our first presenter. That'd be Dr. Paul Addy. He is with Augusta University School of Computer and Cyber Sciences. All right, Mr. Addy.
Thank you. Okay, I'm going to talk about my ideas for documenting and analyzing code to maximize the effectiveness of system design and coding. Okay, so code is hard to understand. It's hard to deal with. It's tricky, it's buggy, it's discontinuous. A tiny change can have huge consequences. Okay, it's very new in that respect. Physical systems generally don't behave that way. And if one bolt rusts out in a bridge, the bridge doesn't come crashing down. Physical systems fail gradually. You can see long beforehand that they're going to fail. You have plenty of time to deal with the problem. Software fails suddenly and randomly. Okay, so how do we mitigate this? You document properly. You maximize your ability to understand the system and what the code is doing. Okay, so there's a huge semantic gap between what the code looks like and how it behaves at runtime. Okay, which again, you don't have with physical structures. You look at a bridge, it's clear what the bridge is supposed to do and how it's going to behave. Same for buildings. With code, poorly documented code can behave randomly, unpredictably. Okay, nasty surprises happen at runtime. Okay, we get exploits and breaches all the time because of this. Okay, so bugs, failures, cost overruns, all of that. Okay, massive chunks of time are devoted to debugging because the code is inherently buggy. Traditional code review was effective a long time ago. Just reading the code was more effective than running it. Okay, which again is an argument for good documentation. But as code bases become bigger and bigger, the effectiveness of traditional code reviews goes down. So you need better documentation. You need automated assistance for documentation. You need many levels of abstraction. Start with a high-level statement of what the code should do, a high-level sketch of how it does it, refine that, okay, until you get down to a level where it's straightforward to turn the comments into actual code. Okay? So code sketching. It's a form of documentation where instead of concentrating on niggly little coding details and declaring variables, you concentrate on the big algorithmic idea. You separate that out, you get that done, and then you worry about turning it into detailed code. Okay? So those two tasks are inherently different. The big algorithmic idea and the detailed coding, they're different tasks. They should be done separately. If you try to do them at the same time, you just make everything harder. Less reliable, more buggy. Okay? Documentation helps to maintain an image of how the code works. It helps with the cognitive workload. Okay? When I write a code sketch, I refine it, then I turn it into code. It's easy. The code has few bugs. Those bugs that exist are quickly correctable because the documentation provides a mental scaffolding for tracing bugs. Okay? I have a tool that I have implemented. Okay, it's an ongoing project, but it manages documentation. You can create a code sketch. It will label the lines in the code sketch, and it will link those to the code which implements that particular line. So if a code sketch says you have to do 1, 2, 3, 4, 5, it will, if you click on one of those, it will highlight the code which actually implements that task. Okay? I use an LLMs to check, does the code actually implement the code sketch properly or not? Okay? So that gives you an early form of verification and validation. It helps you ferret out bugs. It helps you know if your high-level description is an accurate reflection of the actual code. Okay, and by restricting this to small chunks, you can it's humanly verifiable. You can see what the LLM is telling you. You can see if it makes sense. Okay, if you run an LLM on 10 million lines of code, you've no idea if it's telling you something sensible or something incorrect. Okay, so correctness is the main use case. Another use case is refinement. I can give it a code sketch and tell it to give me the code, or I can refine various levels of description. If I have a high-level comment which might be very complex, so I refine that into lower-level comment and then into code, I can check that the more detailed comment implements a high-level comment correctly. And then I can check if the code implements the lower-level comment. So I can refine gradually if I'm doing something very complicated. Okay, I've gotten good results with Claude. The implementation of this tool is in the IntelliJ IDE. Okay, it's basically you create comments as first-class objects. You store them in structures. You can link comments to sub-comments. Okay, and you can link comments to the areas of code which implement those comments. Okay, I have two case studies, buffer overflow and a search engine for searching keywords in documents. I think I have time for only one of those, so I'll do the buffer overflow because that's sort of code from an actual code that's actually in use. Okay, this is actual code that's used to process PNG images. Okay, PNG files contain many chunks for various purposes. Among those are a chunk that describes the color palette being used, a chunk that gives you transparency information, and chunks that give you the actual image data. Okay, the code I analyzed comes from the PNG rutil file. Okay, it's very poorly commented. Okay, this is the actual file that's in active use. Most methods don't have a comment telling you what they do. Almost no method has a comment telling you what the parameters mean. Okay, it's just hard to understand. And code that's hard to understand is hard to debug, and is bug prone. And it becomes more expensive, more time consuming to do anything. Okay, so here's the code. I'm sorry if the font is too small. Wonder if I can. Okay. Yeah, this way maybe I can just. Okay, so here's the code. Basically, it this is driving me nuts. Okay, so you declare a buffer of size max palette length. You check if a PLT chunk has been seen or not. So at this point in the code, you've encountered a transparency chunk. And the constraint is that you've got to have seen a color palette chunk before the transparency chunk, because you've got to know the color information before processing the transparency. So if you've seen this, if you've seen the transparency chunk first, that's an error, you issue a warning. Otherwise, you check if the length of data you're about to read is larger than the size of the palette. That's an error. You return. Okay. never mind. Okay, after that, you read length amount of data into a buffer. Now, the buffer overflow happens because this length constraint, checking if the amount of data being read is too big, only happens in the else branch. So if you go through the if branch, you'll issue a warning, go past the if statement, and if length is too long, you'll get a buffer overflow. Okay, so that's a problem. Okay, the if branch inspects and issues a warning. The else branch checks the size. Okay, it's not tested on the if branch, but it's used in either case, and so that's a problem. Okay, so basically I ran a query which said, is this piece of code susceptible to a buffer overflow? Now, one interesting thing about using LLMs is you run the same query, the answer will change. Okay, so I kept running the query, waiting for a fixed point. Okay, here's the query. Is the code below susceptible to an overflow? Assume. So I'm telling it, well, the size of the palette is bounded by the max palette length. That's, again, a basic constraint. And I tell it to pay attention to control flow. Because the problem here is you should have one if, two ifs in sequence rather than an if else. Okay, so I'm alerting it to pay attention to that. First response says code is fine. Right. Obviously, that's wrong. Second response says, okay, there is a problem, and it identifies the problem correctly. Okay? That you're not checking the length in all cases. Okay? But what it suggests as a fix is, well, in the if case, do an early return also. Which means that in either case, you're going to return, which means execution never goes past this if statement. Obviously, that's undesirable. That's not the right fix. Okay, the right fix is to have if and then if. Okay, third and fourth responses change the else condition, but they maintain the else. Okay, fifth response adds more checking before, but again, early return, which is not what is required, and the sixth response adds another early return. So none of these responses, so it doesn't converge to a defined fix, and all the fixes it gives are wrong. Okay? The next thing I did, I said, okay, instead of asking it to check the code for an overflow, I'm going to give it a code sketch. Okay, and the code sketch is going to be what is going to be this, which is where I basically say, okay, if a PLC starts something, issue a warning, and then if the length is too large, issue a warning return. Okay, the code sketch contains kind of the correct idea. But because it's only a sketch, it's much easier to write down the correct idea in a sketch than in actual code. Okay, that's the point of this. You get the algorithm correct, and then you check it against the code you've written. Okay, and this is the same code repeated. Now, first response tells me, yeah, it's fine, right? Okay. Second response says, okay, checks are combined into an if-else-if structure, which is wrong. Okay. And it gives me the fix. And the fix is to do if no PLC thing issue a warning, and then if length is too large, issue a warning in return. So that's the correct fix. One if followed by a second if. And what's interesting is that the successive responses converge. They all give the verbatim same code fix. Some of the intro verbiage is a little different, but the meaning is the same, and they've all converged to exactly the same code fix. Okay? So by using a code sketch, you've guided the LLM to converge much quicker and you get a correct bug fix, as opposed to when you're just using a vague high-level description of the property you want, it just goes all over the place. Okay. ChatGPT gave similar results for when I'm asking it to check for overflows, but it gave worse results when I'm asking it to check against the code sketch. So another lesson is use multiple LLMs. You don't know a priori which one's going to give you the best answers. And the check for when an answer is good is it keeps giving you the same answer. Okay. Another case study is a document search engine. I don't think I have time to go through all of this, but here the idea is, so you've got a bunch of documents in a database, and you've got keywords, and you want to run all the keywords through all the documents, count the number of times the keywords all occur, and rank the matches. And a document matches if all the keywords occur at least once, and the best match is the one where the sum total is the highest. Okay? If I add a new keyword, I want to process that keyword against the existing matches. Okay, that's complicated. But notice, if I say, what are the inputs? Collection of documents, the query result for the existing keywords, the next keyword. What is the output? The list of documents that contain all the keywords, including the new one, ordered by occurrence count. Okay? Specify your inputs, specify the required outputs. I go through the PNG RUtils file. There is no method where this is done. I mean, how are you going to debug code if you haven't even documented what your methods are supposed to do in the first place? Okay? Another scenario is adding a document. When I add a document, if there's a query in progress, I want to check if the new document is a match, compute the match, compute the occurrence count for the new document, and insert it in the right order in the existing matches. In order to do this with reasonable efficiency, I need to use hash tables and reasonable data structures. Okay, so I've got to describe those. Okay, so these are the major methods: adding a new keyword and adding a document. Okay, I have a word table, which is a hash table mapping words to the documents they occur in, plus, so a word W is mapped to a paired DC, which tells me W occurs in document D C number of times. So you get a list of all the documents the word occurs in. Okay? So now I can say, okay, when I'm adding a new, with an initial keyword, I just look up the matches. It's straightforward. With a new keyword, I add it to the list of keywords already processed. I look it up. For each document that W occurs in, put it in a hash table. That is a hash table just about W. Okay? And now I go through the existing documents, the existing matches, and I look up each document in the hash table. That tells me that that document not only matches the existing keywords 1 through k-1, but it matches the new keyword. Therefore, it is an overall match. I get the occurrence count for WK, the new keyword, add it to the existing occurrence count, and then resort. Now, notice I can say all this in words. I don't need code. Okay? You got to learn to say it in words. Okay? When I'm teaching a class and I tell people, well, here, how do you sort an array? And students start off, well, for I equals 1, 2. No, I don't want to hear for, I don't want to hear I. Tell me in words. If you can't describe it in words, you're not doing the right thing. If you can't describe your idea in words, then go back and, think harder. Okay? Adding a document. Okay? Get the number of occurrences in D of all the keywords. If all the keywords occur, it's a match. Add it in with the appropriate count. Otherwise, leave the existing matches unchanged. Okay? Now, again, I can check. Here's the code. Sorry, it's too small for you to read, but here's the code sketch that you've already seen before, and here's the code. And it will tell me, yeah, it is generally okay, but there are some null checks you haven't done, and there are some discrepancies, which essentially, if you look at it, it requires a fix in the sketch. So this will also help you find, vagueness and missing pieces in the sketch. Maybe the sketch needs changing, not the code itself. Here's another case where I flipped the B. The B here is tracking if the document is a match. For each keyword, I check, and I add it into the B. If all the keywords occur, the B remains true. If the B is false, I do an early return because there's nothing left to be done. Here, I flipped it around. I changed it. That if B is true, I return, meaning if the document is a match, I return. That's incorrect, of course. It figures it out. The initial Boolean check should be inverted. Okay? I ran it again just to make sure. Yes, it still tells me that. Okay? So you can use this. It'll help you with your code. You can document the code. The code is much more understandable. And you can use the LLM to tell you interesting things about the code. Here is, yeah, I know this is way too small to be useful, but basically, these are code sketches, and these are labeled. If you click on this, it will take you down to the piece of code which actually implements that particular line. So you can check each line against the code which is responsible for it. Yeah. Okay. Okay, so that's how that works. Okay. Future work is basically improving the code tracking functionality so that, because here you'll see that a code sketch line occurs at the top as part of the code sketch, but it's also repeated with the code that implements it. So here's CS 1.1, set keys to the single string W. It's repeated here together with the code. Keys equals new string, 1 key 0 equals W. So the same code sketch line also occurs in the code. Now what I want is if I modify this, it links to that and changes it also, or it alerts me. If I change the code, it alerts me. You change the code, inspect the corresponding code sketch to see if that should also be changed, and vice versa. If you change a code sketch, inspect the corresponding code. So that way it alerts you to keeping things, the documentation consistent. Okay? So automated support for code reviews, track design documentation and changes. Things that are changing very frequently might be problem areas that need to be looked at more closely. Okay, right, based on stability. Documentation provides you design at the coding in the small level, designs for individual classes. Okay, code reviews can be targeted to things that are problematic, that change, or that where the LLM is telling you it's not consistent. Okay, you get an audit trail. Design in the large is something I want to handle next. If I have a whole system with hundreds of classes, how do I handle that? How do I handle large distributed software? Okay, but if you can't handle individual classes, you sure as hell can't handle the large systems. Okay, so those are my ideas. If you have problems that you think might benefit from this, please drop me a line. My email is pattie@augusta.edu. Okay. Thank you. Any questions? Okay. Thank you.
Thank you, Mr. Addy. We'll get set up for our next presenter.